And first of all, let's evaluate the zeroth order energy. The zeroth order energy is 0. Our zeroth order Hamiltonian, 0. Now, with our choice of partitioning, this being the Hartree-Fock Hamiltonian, the sum over all Fock operators, which then means that these, our unperturbed states, are all the Slater determinants which we can make from our Hartree-Fock orbitals. And we're still assuming that we're looking at the ground state, correction to the ground state. Then our zeroth order wave function is the unperturbed state with the lowest energy, and that's our Hartree-Fock wave function. So this is actually just our Hartree-Fock or SCF, whatever I called it last week, H0 SCF. And what is that? Yeah, this is precisely what we have. This is the E0, which is now really the sum over all the orbital energies. Did I use epsilon? Yes, orbital energies, epsilon, of the occupied orbitals, the orbitals occupied in the Hartree-Fock determinant. So that's our zeroth order wave function in Møller-Plesset, zeroth order energy in Møller-Plesset perturbation theory. And this is very big, not the same as the Hartree-Fock energy. Yeah. Which means the Hartree-Fock energy is actually not the zeroth order energy, although we use the Hartree-Fock Hamiltonian as our unperturbed Hamiltonian. I mean, this is just the sum over the Fock operators here. And we have the Hartree-Fock wave function, but we don't get the Hartree-Fock energy. The Hartree-Fock wave function is an eigenfunction of the Hartree-Fock Hamiltonian, but the Hartree-Fock energy is not the eigenvalue. Now, what is the Hartree-Fock energy? How do you calculate the Hartree-Fock energy? I mean,
it's the sum of orbital energies minus half of the repulsion, because we count the repulsion twice.
Right, let's talk about that then. Why do we count the repulsion twice if we sum over the energies of the occupied orbitals? Let's look at that. This is sort of, that's the Fock operator for one electron. In that Fock operator, I have the interaction with the nuclei and the kinetic energy. That's not the problem here. Here I have the interaction with all the other electrons described by their orbitals. So here I have the interaction of the one electron, I'm looking at, as Emil said, with all the other electrons. But now I sum over all electrons. So if I start with electron 1, here I have the interaction with electron 2, 3, 4, 5, up to n. That is included in the orbital energy of electron 1. Now I come to the orbital energy of electron 2. The orbital energy of electron 2 includes the interaction with electron 1, once again, and then electrons 3, 4, 5, 6. So I get that interaction between the electrons twice, because it's included in each orbital energy. For some of them I have it double counted. So that's absolutely right that this is not a very good value for the energy, because I have the interaction twice. And luckily enough, the Hartree-Fock energy corrects for them and removes that extra double count the interaction. But how do I calculate the Hartree-Fock energy, actually? How's the Hartree-Fock energy calculated? It's obviously not calculated as the expectation value of the operator with its own eigenfunction, which is a bit strange. This is the sum over the Fock operators. H0 is the sum of Fock operators. How do I calculate the Hartree-Fock? I do it with SCF, like this. But what do I have here? Emil?
The Hamiltonian.
The full Hamiltonian. So the Hartree-Fock energy is not the eigenvalue of that Fock operator, or Hartree-Fock operator. It's the expectation value with the full Hamiltonian. And that wave function is not the eigenfunction of that operator. It's the eigenfunction of that operator. So, and if we do that, we get precisely as we discussed before, we get the sum over the orbital energies. That's one way we can write it, sum over all the orbital energies, the occupied ones. And then we get 1/2 sum over ij, j, what is called ij minus k ij, these now being integrals. So this is the double counting removed. It's half the interaction which is in there, which we subtract again. So the Hartree-Fock is not the zeroth order, and the Hartree-Fock energy is not the eigenvalue of that operator, which we use to calculate the orbitals and the states, the wave functions. Let's look at the first order energy. Well, the first order energy from before, we saw the first order was now the expectation value of the perturbation operator, H prime, with the zeroth order, the unperturbed wave function. Now there are two ways I could do that now. I could insert this one here, and let's do that first. I mean, that's our perturbation operator. So I get 1/2, and let's let that in there, 1/2 sum over I, and should be j, of 1 over Ri minus Rj, 0, minus that thing, which is sum over ij, and now I have j operator minus kj, the Coulomb minus the exchange operator. Now again, that 0 of course is our Hartree-Fock, our SCF wave function. It's a Slater determinant with the orbitals which give the lowest energy, or which give actually the lowest sum of orbital energies. But those we have, you should have looked at actually when you did Hartree-Fock. That is precisely equal to sum over ij, jij integral minus the kij, the Coulomb minus the exchange integrals. And this is the same. Which means that this first order correction is actually minus 1/2 sum over ij, these Coulomb minus exchange integrals. So if we combine them, if we go for an energy which is if we go for the sum of a zeroth order plus a first order energy, the zeroth order I had standing all the way up there. The zeroth order is the sum of the orbital energies. I, epsilon I, occupied. The first order energy correction is minus 1/2 sum over ij, jij Coulomb integral minus an exchange integral, ij. And have you seen that before? That is the Hartree-Fock energy. So the Hartree-Fock energy is actually, in Møller-Plesset perturbation theory, Hartree-Fock energy is actually the energy correct to first order. And that's sort of basically, in a way, the message of the original paper. Hartree-Fock is correct to first order. It is the first order energy. So if you want to have a correction to Hartree-Fock, you have to go to second order, because it itself is already first order. Before we go for the break, I just try to show you the other way we could have done that to get there instead of assuming that you can remember from Hartree-Fock theory how you calculate those matrix elements, expectation values. And that is, we could have used this one instead of this one. I use the explicit form of the operators, put them in, and then assume that you can remember how to calculate those integrals. Let's take this part, because there I can do now for the h prime. I can h prime 0 is then h is SCF. H prime is the full Hamiltonian. SCF minus SCF of the unperturbed Hamiltonian, which is the sum over the Fock operators. SCF. And then we can say, okay, this is Hartree-Fock theory. That's Hartree-Fock energy. That we know is the sum over the orbital energies. And so we can actually come to there from this, seeing that the Hartree-Fock energy is the sum of the orbital energies plus the first order correction.